Okay, so let's look at the solution to the second Manning's equation practice problem. So it's lot simpler in some ways. We want to calculate, there are a couple differences. We want to calculate the specific discharge now, okay, not the velocity. And it's in the English unit of cubic feet per second. And the stream is described as a sluggish wide stream on the floodplain that flows through medium to dense brush. And the channel, as measured on August 2nd, this is important, so it's the summer, is approximately rectangular with a width of 35 feet and a depth of 3.9 feet. So let's first try to figure out, okay, actually, let's start here. In the English units, the Manning's equation gives the average velocity of the stream. Looks almost the same, except we have a factor of 1.5 here instead of 1. So 1.5 over the roughness coefficient times the hydraulic radius to the 2/3 power times the square root of the slope of the stream. So we just have to find the values for n and the hydraulic radius and the slope, and we're essentially done. Actually, we just get the velocity. And then remembering that the discharge is equal to the average velocity times the area, we can calculate the discharge, because that's actually what we're asked to do here. So first, let's figure out the roughness coefficient. So again, we have a sluggish wide stream that flows through medium to dense brush in the summer. So if we look on here, we have on the floodplain, so we're down here on the floodplain, medium to dense brush in the summer. Here we are. So we're at the very bottom of this table. And the normal value of the roughness coefficient is 0.1. So that's what we're going to use. So we're going to say that the roughness coefficient here, n, is equal to 0.1, reading that off the table. Let's do our stream slope here. The slope is the change in elevation divided by the distance. So it drops 35 feet per mile. And you have to know how many feet are in a mile. I happen to know that by heart. So it's 35 feet per 5,280 feet, and that's just a division, and that turns out to be 0.00038. All right, so that leaves us with the hydraulic radius. Now, fortunately, in this case, it's really easy because our channel is approximately rectangular, right? So it's got a width is equal to 35 feet and a depth, this is obviously not the scale, of 3.9 feet. So remember, the hydraulic radius is the ratio of the area of the channel to the wetted perimeter of the channel. The wetted perimeter is the part in contact with solids, and so it's this distance here. So the wetted perimeter will equal 3.9 plus 3.9 plus 35, and that equals 42.8 feet. And the area, well, the area is even easier. The area is just equal to 35 times 3.9. These are both in feet, and that is 136.5 square feet. So the wetted perimeter, the hydraulic radius will equal 136.5 square feet divided by 42.8 feet, and that is 3.19 feet. So I think we have everything we need, right? The average velocity is going to equal 1.5 over the roughness coefficient 0.1 times the hydraulic radius was 3.19 feet to the 2/3 power times the square root of 0.00038, and I put those into my calculator, or in this case my spreadsheet, and I get 0.633 feet per second. Remember, this is the average velocity, but I'm asked to get the specific discharge. Actually, not specific discharge. This should be discharge. I'll fix that on the problem. So calculate the discharge Q. So I just multiply the average velocity times the area. I have both of those things. What are the area? There's the area here. 136.5. So the discharge Q will equal 0.633, that's feet per second, times 136.5 square feet. And I get, final answer, 86 feet cubed or per second, or CFS, right? That's what so there's my final answer, 85. Can you see that? Maybe it's not clear here. 86, sorry, 86 CFS is my final answer for the discharge of my stream.